Hello my lovely students, you're welcome to a new lesson. Today, I shall be teaching you probability. From definition, probability or chance is defined as a measure of the likelihood of an event happening or not happening. Probability is the likelihood of occurrence of an event. The formula for probability is number of required or successful outcomes divided by total number of possible outcomes. Let's learn more about probability. The various types of probabilities are as follows. Number 1, experimental probability. Number 2, theoretical probability. Number 3, combined probability, talking about mutually exclusive events and independent events. And number 4, conditional probability. In this lesson, we shall be learning about the first two types of probability, which are experimental probability and theoretical probability. Number 1, experimental probability. This is the probability calculated by carrying out an experiment or survey repeatedly. For example, tossing a coin or throwing a die repeatedly. Experimental probabilities are not exact or absolutely accurate because if the same experiment is repeated or performed by another person, the result may be different from the first one. Number 2, theoretical probability. This is the probability calculated without experiments performed, but based on equally likely outcomes. For example, tossing a coin once, you will get two possible outcomes, which are a head or a tail. The theoretical probability of getting a head is 1 in 2, or 1 over 2, which is half, or 0.5, or 50%. Theoretical probabilities are exact or absolutely accurate values, which can be calculated by considering the physical nature of the given situation. Please take note of these two types of probabilities, which are experimental probability and theoretical probability. Next, let's take note of the following points about probability. Point number 1. The probability of an event that is impossible or will definitely not happen is 0. Point number 2. The probability of an event that is certain or will definitely happen is 1. Point number 3. If P is the probability of an event to likely or unlikely happen, then P lies in the range 0 is less than or equal to P is less than or equal to 1. That means P lies between 0 and 1. Hence, probabilities less than 0 or greater than 1 do not exist. Point number 4. If P is the probability of an event happening, then P prime is equal to 1 minus P, where P prime is the probability of the event not happening. Once again, please take note of these points about probability. Next, let's see some solved examples about experimental probability. Example 1. A die is rolled 200 times. The outcomes obtained are shown below. From the frequency table displayed here, the numbers in a die are 1, 2, 3, 4, 5, and 6. The number 1 appeared 25 times, the number 2 appeared 30 times, the number 3 appeared 45 times, the number 4 appeared 28 times, the number 5 appeared 40 times, and the number 6 appeared 32 times. Find the experimental probability of obtaining a question A 2, question B 5, question C 6. Let's see the solution to question 1A. Before we do that, can you still remember the formula for probability? Let's see if you can. The formula for probability is number of required outcomes divided by total number of possible outcomes. I hope you got that right. From the question, the total number of possible outcomes are 25 plus 30 plus 45 plus 28 plus 40 plus 32, which will give us 200. To find the probability of obtaining a 2, the number of required outcomes for a 2 is 30, while the total number of possible outcomes is 200. So the probability of obtaining a 2 is 30 divided by 200, which will give us 3 over 20 or 0.15. Using the method explained in the solution in example 1A, can you find the probability of obtaining a 5 in example 1B? Let's see if you can. The probability of obtaining a 5 is 40, representing the number of required outcomes for a 5, divided by 200, representing the total number of possible outcomes. That should give us 1 over 5 or 0.2. I hope you got that right. From the previous explanation, what do you think will be the probability of obtaining a 6 in the solution to question 1C? Let's see if you are right. The probability of obtaining a 6 is 32, representing the number of required outcomes for a 6, divided by 200, representing the total number of possible outcomes. That should simplify to 4 over 25 or 0.16. I hope you got that right again. Next, let's see our second example for experimental probability. Example 2. A statistical survey shows that 28% of all men take size 9 shoes. What is the experimental probability that your friend's father takes size 9 shoes? Let's see the solution to example 2. The probability that your friend's father takes size 9 shoes is equal to 28%. That means 28 over 100, which should simplify to 7 over 25 or 0.28. Let's see our third example on experimental probability. Example 3. Out of every 1,000 cars, 50 develop mechanical faults within 3 months of purchase. What is the experimental probability of buying a car which will not develop a mechanical fault within 3 months? Let's see the solution to example 3. The probability of buying a car which will develop a mechanical fault within 3 months is 50, representing the number of required outcomes, divided by 1000, representing the total number of possible outcomes. This will simplify to 1 over 20. Hence, the probability of buying a car which will not develop a mechanical fault within 3 months will be 1 minus the probability of buying a car which will develop a mechanical fault within 3 months. That should be 1 minus 1 over 20. That will give us 20 minus 1 divided by 20, which is 19 over 20 or 0.95. Please take note of all these solutions for these examples involving experimental probability. Next, let's see some examples on theoretical probability. Example 4. Jane throws the first 6-sided die. What is the theoretical probability that she throws A 9, B a 4, C a number greater than 2, D an even number, E either 1, 2, 3, 4, 5 or 6, and F neither 3 nor 5. Let's see the solution to question 4a. Once again, can you remember the formula for probability? Let's see if you can. The formula for probability is number of required outcomes divided by total number of possible outcomes. In a first 6-sided die, the possible outcomes are 1, 2, 3, 4, 5, and 6. That makes the total number of possible outcomes to be 6. The probability of throwing a 9 is 0, representing the number of required outcomes for a 9, divided by 6, representing the total number of possible outcomes. That makes the probability of throwing a 9 to be 0. That means it is impossible to throw a 9 because there is no 9 in a first 6-sided die. Moving on, for the solution to example 4b, can you tell the probability of throwing a 4? Let's see if you can. The probability of throwing a 4 is 1, representing the number of required outcomes, divided by 6, representing the total number of possible outcomes. That makes the probability of throwing a 4 to be 1 over 6. I hope you got that right. For the solution to example 4c, can you tell the probability of throwing a number greater than 2? Let's see if you can. To find the probability of throwing a number greater than 2, the required outcomes greater than 2 are 3, 4, 5, and 6. These are 4 numbers. Hence, the probability of throwing a number greater than 2 is equal to 4, representing the number of required outcomes, divided by 6, representing the total number of possible outcomes. This will simplify to 2 over 3. I hope you got that right. Next, for the solution to question 4d, what will be the probability of throwing an even number? Let's see if you are right. The required outcomes of even numbers are 2, 4, and 6. These are 3 numbers. That makes the probability of throwing an even number to be 3, representing the number of required outcomes, over 6, representing the total number of possible outcomes. This will simplify to 1 over 2. I hope you got that right. Next, for the solution to question 4e, can you tell the probability of throwing either 1, 2, 3, 4, 5, or 6? Let's see if you are right. The probability of throwing either 1, 2, 3, 4, 5, or 6 is 6, representing the number of required outcomes, divided by 6, representing the total number of possible outcomes. That gives the probability to be 1. In other words, it is certain to throw either 1, 2, 3, 4, 5 or 6 in a fair 6-sided die. Lastly, for the solution to example 4F, can you tell the probability of throwing neither 3 nor 5? Let's see if you can. The probability of throwing either 3 or 5, which are two numbers, the probability is 2 representing the number of required outcomes divided by 6 representing the total number of possible outcomes. This will simplify to 1/3. Next, the probability of throwing neither 3 nor 5, that is not 3 and 5. The probability will be 1 minus the probability of throwing either 3 or 5. That will give us 1 minus 1/3, which is 2/3. I hope all the solutions to example 4, they are all clear to you. Moving on, let's see our next example on theoretical probability. Example 5. A letter is chosen at random from the English alphabet. Find the theoretical probability that it is A, F, B, F or T, C, one of the letters of the word frequency, D, not one of the letters of the word table. Let's see the solution to question 5A. The formula for probability is number of required outcomes divided by total number of possible outcomes. The total number of possible outcomes of English alphabet is 26. Since we have only one F in the English alphabet, the probability that F is chosen is 1/26. Next, let's see the solution to example 5B. The number of required outcomes of choosing F or T is 2, because these are two letters of the English alphabet. Hence, the probability that F or T is chosen is 2 representing the number of required outcomes divided by 26 representing the total number of possible outcomes. That will simplify to 1/13. Next, let's see the solution to example 5C. The letters of the word frequency are F, R, E, Q, U, N, C, Y. These are 8 letters. Please note that in the word frequency, the letter E is repeated. However, we are going to take it as one letter and not 2 letters. That makes the probability of choosing one of the letters of the word frequency to be 8, representing the number of required outcomes, divided by 26, representing the total number of possible outcomes. This will simplify to 4/13. Lastly, let's see the solution to example 5D. The number of required outcomes, which are the letters of the word table, is 5. That makes the probability that one of the letters of the word table is chosen is 5/26. Hence, the probability that not one of the letters of the word table is chosen is P prime for table is equal to 1 minus P for table, which represents the probability of choosing one of the letters of the word table. That makes the probability that not one of the letters of the word table is chosen to be 1 minus 5/26. That gives us 26 minus 5 divided by 26. Our probability here is 21/26. 26. I hope all the solutions to example 5, they are all clear to you. Let's see our last example for theoretical probability. Example 6. A bag contains 2 black balls, 3 green balls, and 4 red balls. A ball is picked from the bag at random. What is the probability that it is A. black, B. green, C. red, D. yellow, E. not black, F. either black or red? Let's see the solution to example 6a. The formula for probability is number of required outcomes divided by total number of possible outcomes. In question 6, the number of black balls is 2, the number of green balls is 3, and the number of red balls is 4. Adding all the balls together, the total number of balls is 9. In example 6a, the probability of picking a black ball is 2, representing the number of required outcomes, divided by 9, representing the total number of possible outcomes. The probability of picking a black ball is 2 over 9. Moving on, can you tell the probability of picking a green ball for the solution in question 6b? Let's see if you can. The probability of picking a green ball is 3, representing the number of required outcomes for green balls, divided by 9, representing the total number of possible outcomes. That will simplify to 1 over 3. I hope you got that right. Next, can you tell the probability of picking a red ball in example 6c? Let's see if you can. The probability of picking a red ball is 4 over 9. I hope you got that right. Moving on, for the solution to question 6d, can you tell the probability of picking a yellow ball? Let's see if you can. The probability of picking a yellow ball is 0, representing the number of required outcomes, divided by 9, representing the total number of possible outcomes. That gives the probability of picking a yellow ball to be 0. In other words, it is impossible to pick a yellow ball because there is no yellow ball in the bag. Moving on, can you provide the solution to question 6e, which is the probability of picking a ball that is not black? Let's see if you can. For the solution to question 6e, the probability of picking a ball that is not black is equal to 1 minus the probability of picking a black ball. That should give us 1 minus 2 over 9, which is 7 over 9. I hope you got that right. Lastly, can you provide a solution to question 6f, which is the probability of picking either a black or a red ball? Let's see if you can. For the solution to question 6f, the probability of picking a ball that is either black or red is the probability of picking a black ball plus the probability of picking a red ball. That should be 2 over 9, representing the probability of picking a black ball, plus 4 over 9, representing the probability of picking a red ball. Adding up these two probabilities will give us 6 over 9, and that will simplify to 2 over 3 as our final answer. I hope you got that right. Please take note of all the solutions of these solved examples involving experimental and theoretical probability. Thank you very much for going through the lesson today. I want to advise that for you to get more information about the topic probability, please continue to read your textbook. Don't forget to attempt your quiz and your assignment. I hope to see you again in our next class. Until then, it is goodbye for now. Thank you very much.